All right, so let's look at this problem. We want to find the maximum positive moment that can be developed at D. So we're going to do moment. And we have a bunch of different load combinations. We've got a concentrated live load, so we've got a 4-kip load that's moving around. We have a uniform load, live load of 300 pounds per foot. Now that's a little bit different. So this live load can actually, believe it or not, it can move around too. And I'll show you how to handle that when we get to this. And then we'll have one we've seen before, a dead load. So that dead load would extend across the whole structure. So the first thing I want to do is find my moment influence line for the moment at D. So like we've done previously, I'll draw this beam out. So we've got a pin at A, we've got a hinge at B, a roller at C, and another roller here at E. So there's the original beam. Now remember, if I use my Mueller-Breslau principle, what I'm going to do is come here to D, the point I'm interested in. I'm going to take the beam's ability to withstand moment away by putting a hinge, and then I'm going to imagine positive bending moment on each edge. And let's see how that would move. So if you just look at this point right here, this hinged point, do you think it's going to move up or down? It's going to go up. So based on that, then it stays here. Got to be connected. It's going to seesaw over C, and then hinge at B, and come back. So there's the qualitative shape of my moment at C influence line. So now I'm going to redraw it. Again, a little more detail. So there's our position X. Our Y, our ordinate value, will be the moment at D. And I'll kind of mark off these critical points. And I'll go ahead and sketch back in the shape. And then we're going to have to decide what we're going to do. So, let me put in the value. So this is 5 feet, 5 feet, 5 feet, 10 feet. So now you have a choice. The easiest thing to do is going to be find one of these points, either this maximum value here or this minimum value here. I don't know which one will be easiest. I have a feeling it's going to be this one. But really what we're looking at, if I want to find this value here, that would be my unit load at 5 feet. And at 5 feet would be right over B. So imagine a unit load at B, and I'm trying to find the moment at D. Okay, that would be one scenario. The other scenario would be this point, this positive point, and that would be over D itself. So the unit load would be over D, and I'm trying to find the unit load at D. I think that one's going to be easier to deal with. So what I'm going to do is I'm going to come back up to my structure, and I'm going to have to take it apart here at B anyway and have a free body diagram for AB and then a free body diagram for B, C, D, E. Because you'll notice I have two unknowns at a pin, one more at a roller, another at a roller. I can't solve the whole free body. So let's just do this, and maybe you'll be able to see a little better. So if I draw the AB section, what would I have? Well, I have a pin at A, so that would be AY, AX. Now I'm going to come here, and I'm going to assume, I've got a positive shear here. That would be the shear at B. And then on the right-hand side, I have the same positive shear there. What else do I have? Well, I've got this reaction at C, which is about right here, and this reaction at E, which is about right here. So imagine, again, I'm trying to find this value, so that means my unit load would be at D, which would be right about here. So these dimensions are 5 feet, 5 feet, 5 feet, 10 feet. Now I'm going to eventually try to find the moment at C. I'm sorry, D. So think about this. If I can find, if I then cut the structure at that point, which side would be easier to work with, the left side or the right side? I think the right side. So that means all I need is EY. So how do I get EY with this scenario? Well, it's not as bad as it looks. If you look over here at this free body diagram, there are no applied forces. There are no applied moments. So what are all these forces equal to? Zero. So if the shear at B is 0 here, what's the shear at B there? 0. So that means all I have to do to find EY is sum moments about C. So if I sum moments about C, make sure it's in equilibrium, what do I have? Well, about C, remember B, this is 0, right? This is 0. This is 0. Then all I have is this force, which creates negative moment, so that'd be minus 1 times 5 feet. And then EY creates positive moment. And from C, that would be EY times 15. So what's EY equal to? Looks like 1/3. Okay? So now if I cut this structure at C, D, thank you. This part is 10 feet. So my reaction EY is 1/3, and I'm looking for the moment at D. I just like to remind you that the unit load is still there, but you can see it doesn't have any effect about the moment when I sum moments about the cut. So again, if you sum moments about the cut, set it equal to 0, what do I get? Well, my internal moment is negative. About the cut, my reaction creates positive moment. The force is 1/3, the distance is 10 feet. So it looks like the moment at D is 10/3. So that means this value is 10/3. If this value is 10/3, what's this value? Well, they both have the same base, similar triangles. If you're having trouble seeing that, I'll draw it like this. That triangle is the same as that triangle. And they both have the same base, so they must have the same height. But this is negative, so this will be minus 10/3. So there's your influence line for the moment at D. So now I got 3 things to take care of. Two uniform loads and a live load. Let's do the let's do the new one we haven't done before. Uniform live load. So here's going to be my uniform live load. So the new thing about this is it does have a value of 300 pounds per foot, but where do I put it to create the maximum positive moment? Well, I don't want to put it over the negative areas because that creates what kind of moment? negative. I only want to put it over the positive area. And that will start here at 10 feet in and go to 25 feet. So I'm just going to do the positive area. So that means I'm going to start off with 300 pounds per foot. That's the load. It's a triangle, so 1/2. The base is 15 feet. And the height is 10/3 feet. I left my unit off here. This is feet, and all these units will be feet. So somebody's got, let's see, I'm going to need some help with that. Let's see, it's 150 times 300 divided by 6. What's that? We'll see that 6 makes that 50. 50 times 150. 2,500. I'm guessing. No, not close. How much? 7,500. Everybody else get that? So that'll be 7.5 kip feet. So that's the only thing that's new. The rest will be just like before. So now I've got a uniform dead load. Now dead loads don't move around. They may be just the weight of the structure. So they have to extend the whole beam. So that will include both negative areas and positive areas. The dead load is 200 pounds per foot. Again, it'll be 1/2 because it's going to be a triangle. And now I'll take the areas in pieces. So I'll do the first part, which will be the negative area. Has a base of 10 feet and a height of minus 10/3 feet. And then the next area will be this positive area, which has a base of 15 feet and a height of positive 10/3. What's that? 1,666. I don't know. I just wanted to say 666. Anybody else figure that out? Is it 1,666? Oh, what do you know? So that'll be 1.67 kip feet. Positive. Because the positive part was bigger than the negative part. And then finally now our live load, which was a value of 4 kips. Where should I put the 4 kip to create the maximum positive moment? Positive. So I find the largest positive value, which is right here, 10/3. And where is that? That's right at D. So that will be 4 kips times 10/3, which is 40/3, which is 13.3333. And that will be kip feet. But now you add them all together, and the maximum moment at D will be, what is that, 22.5? 22.5 kip feet. And what does that load look like? Let's see if I can redraw that. So I've got my pin here at A. I've got this hinge at B. Got a roller at C and a roller at E. So let's first start with my dead load. Remember, that goes over the whole structure. So I'll draw that. So there's my dead load. Now where's my live load go? Well, that only goes over what? This positive part. So it'll start here at C and go to D. So it's only going to be over this section of the beam. See that? That corresponds to this part here from C to E. And then finally the live load part here, the concentrated load, we put that right here at D, which would be right here. So this is the load combination that gets this. So our live load was what was it? It was 0.3 kips per foot, and the dead load was 0.2 kips per foot. That's kind of small there. I forgot to add that in. So that's the configuration of the loads to produce this maximum moment at D. So if my live distributed load moved around anymore, if it moved over here, then it would start picking up negative value, and that would lower this amount. All right? And if my uniform load moved to the right, what would happen? Its influence would go down to 0. If it moved to the left, right to point C, again, its influence would go to 0. And if it moved anywhere between A and C, what would it do? It would create negative moment and also reduce it. That's kind of a visual way of showing you how these three loads have contributed to make this the largest value at D. So any questions about that?
My biggest thing is the live load. How do you know it was just like that section?
We always locate the live load over the portion of the influence line that contributes the most. So if you want positive moment, you only put it over the positive part of the curve. See the positive part that goes from here to here? If I wanted to rework this problem and do the negative moment, where would I put it? I'd put it over just the first 10 feet. And my uniform, my concentrated load would be where? Here, which would be at B. Now you'll notice the dead load, I don't get any control over that. So the dead load is going to contribute positive moment no matter what I do. But I think by locating it, I could generate a negative moment. So again, remember, this is all moving loads. So this might be a single axle in a truck that's moving around. This just happens to be, if it stops here, that creates the maximum moment at D. This could be an equivalent of the load of that truck moving around. So again, it could be in a different position and create negative moment at D. So again, bridges are very dynamic in that the moments in the shears, axial forces, all the forces are changing constantly depending as the loads move around. About the stillest they'll be is when there's no load at all on the structure and it's just supporting its own weight. Even then that varies because temperature heats up, cools down, causes the bridge to change shape. Believe it or not, the earth vibrates a little bit. So it's really never static, but very small forces. All right.